Welcome to the Explainer. Today, we're diving into something that sounds like it's straight out of science fiction, building predictive digital copies of human anatomy. We're talking about creating a digital twin that can actually mimic how our bodies move. So let's just start with this idea, because it's a powerful one, and it's driving a huge revolution in personalized medicine. Just imagine a world where your doctor isn't just treating you based on a flat, static picture, but on a dynamic, predictive model of your own body. What if they could see exactly how a tumor is going to shift around as you breathe before they even fire a single beam of radiation? That is the core question we are digging into today.
Okay, so how do we actually get there? Here's our roadmap. First, we'll look at how you turn a flat scan into a 3D shape. Then, we've got to bring that shape to life by modeling its motion. After that, and this is key, we'll ground it in reality by adding the laws of physics. That foundation lets us build the predictive twin itself, which brings us to the big question. What does all this really mean for the future of medicine?
All right, so our journey starts with the very first hurdle, taking a 4D CT scan, which is basically just a movie made of X-ray slices, and turning all those flat pictures into a really high-fidelity 3D blueprint of a patient's anatomy.
So the very first thing you have to do is this process called segmentation. Honestly, you can just think of it like digital tracing. It's about meticulously, and I mean meticulously, outlining every single key structure, from the lungs to the heart, on every single image. That's how you tell the computer exactly where everything is. Now, you can imagine trying to do this for an entire 4D scan. That would take an expert literally forever. So to get both speed and accuracy, researchers use this really clever two-step hybrid approach. First, an AI tool called Total Segmentator zips through and does a fast, automated first pass. Then, a human expert uses another tool, Vista 3D, to come in and perfectly refine the details on just one key frame, creating a kind of gold standard to build from. And this is why these two tools are such a perfect match. You've got Total Segmentator, which is like the workhorse. It's built to just plow through huge amounts of data automatically. Then you have Vista 3D, which is more like the artist's fine-tuning tool. It lets an expert make these incredibly precise corrections with just a few clicks. It's the best of both worlds, really. You get the speed of the machine and the accuracy of the human expert.
And what do you get after all that meticulous work? You get this beautiful set of clean, super accurate 3D surface models, or meshes. And right there, we have our digital blueprint, a perfect, static copy of the patient's anatomy ready for us to bring to life.
Okay, so we've got our static 3D shapes. Awesome. But, our bodies don't just sit still, right? So the next massive challenge is to make these digital objects move realistically, to capture that constant, complex motion of just breathing.
And here is the big problem you hit right away. If you just treat the entire chest area as one single continuous object, you get this really weird, unnatural stretching and distortion. But in reality, your lungs don't stretch with your ribs, they slide against the chest wall. To capture that, you can't use one global model. You have to treat the lungs, the heart, and the bones as totally separate, interacting things.
So how do they solve this? Well, scientists use a process called deformable registration. Now, that sounds complicated, but all it really is a computational way to create a super detailed map, a deformation field that tracks exactly how every single point on every organ moves from one moment to the next.
The solution is super elegant. It's basically a divide and conquer strategy. They break the anatomy down into 4 main groups. You've got the lungs, the heart, the bones, and then all the other soft tissue. A tool called Unigrad Icon then calculates the motion for each of these groups on its own. This is great because it can capture the rigid movement of bone, but also the elastic squishiness of the lungs. Then it just blends all those separate motion maps back together into one cohesive, realistic animation.
So at this point, we have an animation that looks right, but is it physically right? The next absolutely crucial step is to make sure our model doesn't just look like what we see in the scan, but that it also obeys the fundamental laws of biomechanics. And that question is everything, because for a model to be truly predictive, it can't just look the part. It has to be the part. It has to be grounded in the physical reality of how our tissues and bones actually behave under force. The answer comes from this really cool engineering technique called the finite element method, or FEM. The easiest way to think about this is like a physics upgrade for our digital model. FEM gives the digital tissues real-world properties, like how stiff lung tissue is or how much heart muscle resists being compressed. It simulates how they would actually respond to forces. So when you combine the visual data from the scans with the hard rules of physics, you end up creating the best possible training data you could ever imagine. This isn't just a simple animation anymore. It's what's known as a ground truth dataset, a model that is validated by both what we can see and what we know from physics. It is the perfect teacher for an AI.
All right, here we go. This is the final leap. Now that we have this incredibly high-quality, physics-informed data, we can finally do what we came here to do: build an AI that can actually see the future.
You see, this whole really painstaking process, it's all been building to one single incredible goal.
To be able to take just one single static 3D snapshot of a brand new patient and have an AI predict their full, unique respiratory motion over time. To literally see the future of their body in motion, all from just one moment.
So here's how that pipeline actually works. Step 1, you take a single static CT scan from a new patient. Step 2, you feed that image into an AI model that's been trained on all that high-fidelity physics-based data. And because that AI has already learned the universal rules of biomechanics, it can spit out a complete predictive 4D animation of that specific patient's breathing cycle. It's predicting the movie from a single photograph. Okay, so what's the point? Why go through all this trouble to create these predictive digital twins? What does it actually mean for patients in the real world? Well, the clinical applications are just transformative. It really boils down to 3 huge benefits. First up, precision. Doctors can target moving tumors with an accuracy that was never possible before. Second, speed. It can accelerate treatment planning because you don't need to do as many time-consuming scans. And third, and this is the big one, true personalization. Every treatment can be planned based on a dynamic simulation of a patient's own unique body, not some generic model.
And the potential goes even further. I mean, we're talking about radiation therapy that can adapt to a tumor's movement in real time. Imagine surgeons rehearsing a super complex procedure on a patient's digital twin before they ever even make an incision. We could design personalized implants that perfectly fit a body in motion, or even simulate exactly how a new drug will spread throughout a person's unique system.
But at the end of the day, the success of this whole thing comes down to one core principle, which the research just nails perfectly. The AI's performance ceiling, how good it can possibly get, is set by the physical plausibility of the data it's trained on. In other words, garbage in, garbage out. The reason this all works is because the AI is learning from a foundation of reality. The quality of that foundation is everything.
And that leaves us with this final big thought. This isn't science fiction anymore. This is where the science is actually going. So the question we have to ask isn't if, but how is healthcare going to fundamentally change when every single one of us can have our own predictive digital twin? It's a future that might just be closer than any of us think.